Okay, so welcome to our final lecture. All right, so we are finally almost at the end. All right, so after today, basically, and today's tutorial, you just have your project to finish up. All right, and then next week will be assessment. Okay, so I will talk more on that later towards the end. All right, so today's topics very short. All right, so we should finish within the hour, and then we will have some time for discussion on the exams as well as the project. Okay, so let me get started. Okay. Okay, so today's topic is something that I added last the last batch. All right, this address decoding. All right, and why I added it is because when I went around asking many students, I mean your seniors, whether they knew what was address decoding and how to design address decoding circuitry, and everybody looked at me as if they never heard the name before. Okay, so I'm not so sure. From what I heard from the seniors, this topic on address decoding has not been actually taught in other modules. All right, and it's quite shocking because I think as computer engineers, you have to know how to design something like this because you are. I mean, though we are used to using ready-made development boards. Okay, at some point of time you may be having a task to design your own embedded board, at least from the processor level up. So you need to wire up your processor to memory to IO devices and so on. And when you do that, you need to have this concept clear. But how do I map various peripherals to different parts of my address space? All right, so that is currently done for us with readily available development boards. Okay, but you need to know how to do it on your own so that when the time comes, you know what to do. Okay, so that is why I wanted to introduce you to this concept. Okay, and make sure you understand it. And then we'll talk a bit about DMA. Though we did have some idea of DMA in I think EPP, that was very brief, and we'll talk just a bit more on that, and then a bit more concepts on some software areas, and then we'll conclude with that. Okay, so let's move ahead. Now, what is the idea of address decoding or address decoder circuits? Okay, basically, when you say you have a microprocessor system, all right, so we know that, for example, if I generalize it to say I have a CPU here, okay, and that CPU may have memory, okay, I mean the entire embedded board of memory, you have IO, okay, and you have other peripheral subsystems. Okay, so now when you write a code, all right, when you want to talk to memory, you put out some or you want to update some data in the memory or read something from the memory, you need to communicate to the memory through what we call three different uh, sort of set of buses. Okay, so we have the address bus, you have the data bus, and you have the control bus. Okay, but the control bus is usually just a few lines, so we call it control lines, but you have address and data bus. Okay, so when I say I want to talk to the memory region, so there must be some space that I have mapped it to. Okay, so for example, I have mapped my memory to 0x000 to 0x07FF, something like that. Okay, so before I can even do this mapping of addresses, firstly I need to know how big is my address bus. So in this case, let's say if my address bus is 16 bits, that means the full range that I have, okay, the full range that I have to access is from 0000 all the way to FFFF. So that is the full range that I have. Okay, so within this address space that I have, I need to now map all my various subsystems. So for example, in this case, maybe I say my memory, I want to put in this range 0x07FF. Okay, so then maybe my IO, so this is my memory, and then my IO devices all I put to some other memory, so maybe from 0x2000 to 0x20FF something. Okay, so different subsystems will have to be mapped to different parts of the memory. If you look at your what you'll be doing with your KL25Z, your microcontroller, all right, when in the first half, when we did all the hardware level configuration, we dealt with a lot of registers. Okay, but if you look in the header files, all right, you will see that all the registers are mapped to specific addresses. All right, so when I wanted to configure port A, the data direction register, or I wanted to set a bit to 1 or 0, I want to configure the UART at a certain speed. So all of those are registers which are mapped to specific addresses. All right, so this mapping is already done for us, okay, by the person who designed or the team that designed that board. All right, but if you want to do it on your own, then you need to map all these subsystems and their addresses to the address range that the processor has. Okay, so that is the whole idea over here. So how do we go about doing this? So the key thing is every device, all right, must be activated when that particular address is being uh, reflected on the address bus. Okay, so if I have, for example, in my memory, okay, so your memory itself, you may break it up into multiple segments. Okay, so you may have one segment which is a ROM, one section which is a RAM, and so on. Okay, so this could be a particular chip. All right, so this is chip 1, okay, chip 1, and this is chip 2. All right, from your hardware modules, you would know that every chip, okay, when I want to activate it, there's actually what we call a chip select line. Okay, so there'll be a chip select line that I need to activate if I want to talk to that particular component. All right, in most cases, it is an active low chip select, so that's why you put the bar on top. Okay, so when you put the bar on top, it is indicative that it's actually a active low. So you usually put a bubble there. All right, that means only when the chip select pin is in the active state, then that device is actually able to communicate. If not, it goes into a sort of a mode where it cannot send or receive any information. Okay. So how do we make sure that I select the correct device? Okay. So for example, in this two chip design, maybe I say that 0000 to 01FF is my ROM, and I say this is 200200 to 0x2F02FF is my RAM. Okay, that means when on the address bus, okay, so this has to go through some circuit. Okay, this is a decoding circuit. Okay, so it should be two separate lines. Okay, not connected. Then over here, what you get is the address bus. Okay, so the address bus will go to the decoding circuit, and the decoding circuit must tell or activate the correct chip depending on which address is available here. Correct. So if the address available here is, for example, 0x0080, then that maps to this region over here. So I should activate chip 1. Okay. If it is in this range, a second range, then I activate chip 2. All right, so that is the idea of the decoding circuit. And when we say activate, we're talking about the chip select pin. Okay, so how do I do it? The way to do it is you can split up this address line. Okay, so this address line that you have, you split it up into two sections, where the lower sections go directly to the memory and the higher sections go to the decoding circuitry. Okay, so that is how you do it. Okay, later when we look at the tutorial question, you have a better idea how to decide where to split. Okay, where do I draw this line over here? Okay, so where do I draw this line? We will see later. All right, so now let's look at a simple example. So in this example, we have 10 address lines, okay, on the address bus. So if I have 10 address lines, my total space that I can address is 1 kilobyte of memory. All right, so let's assume that now I want to populate this entire memory with 1 to 8 times 8 memory chips. Okay, so this is, I'm going to have 8 separate memory chips to give me that full 1 kilobyte of memory. Okay, so now since I have 8 chips, okay, so I need to be able to generate 8 different chip select lines, correct? So there's chip select 0, chip select 1, all the way to chip select 7. So I have 8 different memory chips. So I must be able to generate 8 different chip select lines, all right, depending on what it is mapped to. All right, so how do I do it? All right, so one of the easiest way to do it is if this number here, okay, you can directly map it to a 2 power. So in this case, we know that 2 power 3 equals to 8. All right, 2 power 3 equals to 8, and we want 8 outputs and 3 inputs. In that case, all right, then what we need to do is, since to generate 8 outputs, I need 3 inputs, I can use a 3 to 8 decoder. Okay, so I believe you all should know what is a decoder chip. Okay, you have learned it in some other module. A decoder chip is basically a chip that takes in an input and activates one of the output. Okay, one of the output lines. All right, so how I can do it is, when I look at the full address bus that comes out, 10-bit address bus, okay, so I've split it up into 3 and 7. Okay, so the 3 is the one that goes to the decoder. So when this upper 3 bits are 0, okay, so if you look down here, the upper 3 bits will be 0 for this first memory 0, but the 7 bits here, the lower 7 bits will go from 0, 0, 0, 0, 0, 0, 0, all the way to 1, 1, 1, 1, 1, 1, 1. So that will be the entire range where the first chip select line will be activated, and that means only the first memory will be activated. All right, then when I go past this address, okay, to let's say I go to where the upper 3 bits become 0, 0, 1, then the same thing happens, correct? That means as long as the upper 3 bits are 0, 0, 1, only the second line will be activated. All the other lines will be deactivated. Okay, so you can see that the lower 7 bits of the address automatically go to all the memory chips at the same time. Okay, but that doesn't matter because at any point of time, only one of the output lines of the 3 to 8 decoder will be active. So if only one line is active, then only one of the chip select will be active. So the rest of the memory will not interfere with our communication. Only that particular memory chip that is mapped to that address will be activated. Okay, so that is basically how you look at it. Okay, so in this example, we can sort of solve this quite easily using this simple 3 to 8 decoder chip. Okay, now in that example, okay, in this example, okay, we have a 10-bit address, correct, and we are using this entire range. I mean this 1K range for this 8 memory chip. So there is no free space at all, right? You're fully allocating the entire memory region to the devices that you have. Okay, but in most cases, all right, there will always be situations where there are pockets of memory that are not used. Okay, when you are doing the design. So similar for any microcontroller. If you look at your KL25Z, the memory map layout from the data sheet, you will also see that there are sections of the memory that are currently unused. All right, that is always the case because you may have a lot more space than you really need. Okay, so in that case, how do you design the address decoding circuitry? So there are two options. One is what we call the full address decoding. The other is what we call the partial address decoding. So what is full address decoding? Now let's look at this same example again. All right, now the same device with 1 kilobyte of memory space, but now I do not want 1 kilobyte of memory. I only want 512 bytes of memory. That means I'm only using half of the memory space or the address space. The other half of the address space is going to be free. So this part here is free. Okay, it's not used. All right, so how do I then do it? So I can still do it the same way. Okay, so I can still use the same 3 to 8 decoder as before. Okay, I can still use the same 3 to 8 decoder. Only thing is I will use either the upper 4 lines or the lower 4 lines, either this or this. All right, so I can still do the same approach. Okay, but of course, in terms of hardware cost, if let's say you want to cut down on cost, you can design your own circuitry. Okay, so I'm sure you all have done your digital logic module, so you know how to map input to output, draw K-map, do simplification, all this stuff. All right, so if you do that, okay, if you do that, you can get some design like this. All right, and in this, you can see that I still am able to take the upper 3 bits and generate the 4 outputs that I want. Okay, or if you go with the 3 to 8 decoder approach, it will still work. Okay, it will still work. Only thing is you use only half of the decoder, the other half is not used. All right, so this is what we call the full address decoding because you use all the bits that are available. In this case, 10 bits of the address bus. You use the full 10 bits to decode and select the correct chip. All right. Now, what is the other option? Okay. The other option is what we call the partial address decoding. Okay, if you look back here, you will see that the A9 bit here is always 0. In this current design, the A9 bit is always 0. Only A8 and A7 are changing. All right. So since only A8 and A7 are changing and A9 is always 0, all right. So can we choose to ignore A9? So if I choose to ignore A9, what will happen? Okay, it will be considered as a don't care condition, all right? And I use only A8 and A7. Okay, so in that situation, what happens is you get the same output. Okay, you can get the same decoding effect, but you have another thing called aliasing. Okay, so this is a typo here. This is 0, this is 1, this is 2, and this is 3. Okay, so aliasing basically means what? That means since A9 is currently not used, regardless of A9 being 0 or 1, it will activate some region in the memory. Okay, that means in this case, when A9 is 0, I will activate this region, which is actually what I want. If A9 is 1, I will activate this region. All right. So you have this issue of aliasing. Now, is this aliasing a real problem for us? It all depends on your whole design, okay, what you're trying to do. Okay, in the situation where you want this memory space for some future expansion, okay, that means you plan that, okay, maybe later on I will use this for memory regions, for some other peripherals and so on, then it will cause a problem. Okay, but if you are already, or you've already finalized your design and you know for sure that this will never be accessed in your system, then it doesn't matter. Correct? So it doesn't matter, because if you know it will never be accessed in the system, then this condition should never occur. Okay, this condition should never occur if you know that that region of memory is not used in your whole system. All right, so this aliasing is just a side effect. It where you have additional memory regions activated uh, while your own one is being activated as well. All right. So uh, if you have expansion plans in the future, then it's better not to do this approach. But if not, then it is fine. Okay, so now how do we implement address decoders? So just now I showed you the idea of using the 3 to 8 decoders, which is this. Okay, and in the simplified example, we saw the use of some discrete logic, and it's AND gates, OR gates, NOT gates, and so on. Okay, of course, these are fairly simple approaches if your memory map is also quite easy. All right, but if you think about our microcontrollers that we use, where you have so many peripherals, so many registers, and so on, it is very complicated to try and design this using this kind of uh, logic blocks. So the easier option would be to go in the direction of what you call a PROM or a FPGA. Okay, so a PROM FPGA, basically what you can do is you can write some code that will translate the memory to some chip select activation. Okay, so if you talk about FPGA, then it is equivalent to writing some code, correct? So you just check if the address that I want is equals to some region, okay? Then you say chip select whatever, okay, is equals to 1 or 0. Or something like that, where you can write some VHDL or Verilog code, okay, in this kind of logical thinking. All right, and when the address maps a particular region, then I activate the chip select and so on. Then of course for FPGAs and those kind of hardware description language, the hardware will be programmed, okay, based on the logic that you provide. Okay, so that is a more feasible approach if you were to talk about more complex systems. All right, if you're just having a few peripherals, okay, and you want to keep the cost low, then using decoders and basic logic gates is more than enough. Okay, so let me just run through this example. Okay, so you have an idea of how this thing works. Okay, so I'm not going to go through the whole decoding, but just one or two of it. Now, if you look at this device here, or this address decoding circuitry, basically you have two decoders with some logic gates as well. Now, let's look at this first decoder here. So this first decoder here is again a 3 to 8 decoder. It has 3 enable pins. Okay, these 3 enable pins means all these 3 pins must be in the active state, then only this decoder is considered to be functional. So the first one is E bar, so E bar is tied to 0, so that is fine. The last one is EE is tied to 1, so it's also fine. And the middle one is E bar tied to A15. That means what? When A15 is equals to 0, is low, then only this chip is considered active. Okay, then only this chip is considered active. So since this is a 16-bit system, because the highest address line is A15, so if you look at it from the address perspective, it's A15, okay, A14, A13, A12, all the way down to A0. So only when it is 0, this chip is active. The moment it becomes 1, this chip is inactive. All right, that means there's no decoding going to happen after that. Okay, that means the smallest address is when it's all zeros. The highest address is when it's 0 and all ones. Okay, so that means this is the region where I'm decoding, and anything from 100 onwards is not used. It's not used. So this translates to what? This translates to 0x8000, all right, which is this region here. Okay, so in this particular design, we are only using half the available address space, where the most significant bit is 0. When the most significant becomes 1s, becomes 1, we're not using that half of the address space. All right, so that gives you an idea of how that entire second half of the region is not being used. All right, now let's just look at one or two of these peripherals here. Now, if you look at the first one, ROM1, okay. So coming back here, you can see that this is a 3 to 8 decoder. Both of them are 3 to 8 decoder. So when it is 0, 0, 0, that means line 0 will be activated. Okay, so when line 0 is activated, okay, then what you have is you are able to say that this region is when it's 0, 0, 0, and everything else is 0. Okay, now when is the next time when it will switch to Y1? When it becomes 0, 0, 1. Okay, so this will be Y0 activated. So when will it switch to Y1? When it's 0, when it becomes 0, 0, 1. Okay, so now this part, okay, you can see that the A14, A13, A12 is basically the CBAA, the 3 to 8 decoder, the 3 bits used to decide which of the lines will be activated. Now, let's look at Y0 and zoom in a bit. So for Y0, we know that it will be activated when all the CBA are 0. Y1 will be activated when CBA or 14, 13, 12 is 0, 0, 1 and so on. Okay, now let's look at this from the hexadecimal perspective. So if I look at Y0, from the hexadecimal perspective, it is 0x, 0. So this will be 0 and all the way 0, 0, 0, 0, all the way to when the highest value. So if I were to break this up here, just before Y1 starts, the highest value will be 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. Make sense? So the highest value for Y0 would be when A14, A13, A12 is still 0, but the rest of the bits are 1. Okay, so the rest of the bits are 1, it will become 0, F, F, F. Okay, 0, F, F, F. So that is the address range for Y0. Similarly, for Y1, it will start when it is 0x, 1, 0, 0, 0, all the way to 1, F, F, F. Okay, so you can see that it breaks up into the address range as specified here, 0, 0, 0, 0. Next one is 1, 0, 0, 0 and 2, 0, 0, 0 and so on. Okay, so that is basically how you can translate, okay, or relate the memory map over here, okay, to the hardware design over here. Okay, so the rest of it I will not go through. You can go through on your own to see how everything works. Okay, but later I'll go through the tutorial question on this. Then you have a better idea how we can design it from the memory map to the decoder. Now what you're doing is you're trying to look at the decoder design and trying to map it to how the memory map layout is. Okay, later in the tutorial question, you will look at the memory map design and map it back to designing a decoder. All right, so this will be the full truth table, okay, of the system. All right, once you map out everything. All right, so and like I said, this is the idea of using the PROM or FPGA where you have some lookup tables or some software that will take the address. Okay, so this is the address coming in and generate or execute some code and things like that to give you the required chip select at the output side. All right, so that is an easier option when you have more complex architecture to deal with. Okay, so this is the range. Okay, so I'm not going to go through this. Okay, so that basically gives you some idea on address decoding circuitry. And like I said, why it's important is because if you ever tasked to do something like this where you have some new peripheral and you are custom building your own board, okay, from the processor level up, then you need to be able to design this kind of circuitry, okay, to map peripheral devices to different ranges in the address. All right, so that is why you need to understand how this works. Okay, so now let me just have a quick overview on DMA. So the idea of a DMA, okay, is basically what we call the direct memory access. It allows you to move data between the CPU memory and the peripheral without using the CPU itself. All right, so if you look at it from the perspective of what a software would do. Okay, so if I have my memory region, okay, let's say this is memory region A, this is memory region B, and I say I want to take all this data and I want to copy it over to here. Okay, so if you want to write a software to do it, what will you do? You need to read the first word from A to some internal register in your code, and then you need to write. Correct, and then you point to the next one, point to the next one, and then keep doing it until you finish. Okay, so if you were to write a software loop, okay, to do something like this, is actually a very wasteful use case of your processor, correct? Because you're just moving data from one place to another without doing anything else that is value add. All right, so that is why the DMA helps us, because if I want to do something like this, where I don't need to do any further processing. Okay, if after I read, I need to do some processing of the data, some signal processing or filtering or things like that. Okay, then there is a value add. Okay, but if there is no value add, it's just moving data around, then it makes no sense to use the CPU. So the DMA is where we can leverage on to make life easier. So what does the DMA do for us? So the DMA basically sits in the middle, where it also has control over the address bus and data bus. All right, so what would happen is, all right, so for example, when you want a peripheral device to wants to do some memory transfer, okay, so in this case, for example, you have a peripheral device, okay, a disk drive, for example, that wants to move a large chunk of memory around. So the peripheral device would send a transfer request. Okay, so this is one use case where the peripheral device is sending a request to the DMA to say that I want to have some data transfer. All right, and then what will happen? The DMA will send a request to the CPU to ask for permission to carry out this action. All right, so once the CPU gives the grant, okay, that means it gives the approval, the DMA will then send the grant or the approval over to the peripheral device. And once that is done, okay, it will now switch the bus. All right, so what it will do is it will now allow the bus switch 1 to be closed, and it will allow bus switch, it will disable bus switch 1 and enable bus switch 2 and 3. Okay, so basically what will happen is it will make sure that the CPU does not interfere now with the address and data bus, and the DMA and the peripheral are the ones that are controlling the bus. Okay, so that is allows you the fastest possible way of moving data around, because you no longer have to do this fetching and writing, fetching and writing and so on. Okay, so everything is handled by the DMA itself. All right, so this is basically one way in which this thing can happen. All right, where the peripheral initiates and then it goes to the DMA controller, CPU, and comes back. All right, and then the whole data transfer happens. Okay, like what I mentioned just now. Okay, the other instance is within the processor itself you want to initiate. Okay, so for example, you have uh, some data that has just come in, okay, through the Bluetooth or through the serial port, okay, and you have this huge chunk of data that you now need to write to the external hard disk of the system. Okay, so you do not want to write or have a software loop to do it. You can now initiate the DMA to do this for you on your behalf. So how can it be done? The CPU will now need to configure the DMA controller first. Okay, so when you say configure the DMA controller, there are three things here. So there is the address registers, the byte count, and control register. So when you say address register means what? That means you need to provide information on where is the source. So technically what we are doing with DMA, okay, we are moving one chunk of data from one place to another place. So I need to know where is my source and where is my destination. Okay, so I need to provide that information in the address register. Then I need to know how big is this size of data. So that is the byte count. All right, and the control register is basically the register where you can configure things like whether you want interrupts, okay, when to start, and so on. All right, so the control register is just like any other peripheral control register where there can be some settings and configurations you can uh, put in place depending on how you want that peripheral to behave. Okay, so generally DMAX or DMAs have two different types of operation. One is what we call the burst mode, the other is called cycle stealing mode. Okay, so in burst mode is basically the one where you have the fastest possible rate of data transfer. Okay, that means once I say burst mode means I will take full control of the address bus and data bus, and I can do all the transfer that I need to do. Okay, so that will give me the fastest response time. The other option that DMA controllers will usually give is what you call the cycle steal mode. So in the cycle steal mode, okay, you in a situation where you want the processor to also be having some time to process and execute instructions, all right, while you are also doing the DMA transfer. So in the cycle steal mode, what will happen is in each cycle, you will alternate between uh, DMA and CPU. Okay, so one half of the cycle, the DMA will use the bus, then the other half, the CPU will use the bus, and so on. All right. So this is again another alternative way in which you can sort of allow the CPU to carry on with some activity while the DMA is also doing its transfer. Right. So all this is transparent to us. If your processor architecture supports it, then you just need to make sure that all your configuration, your settings are all done correctly in the system, and the rest will be handled in the background for us. Okay, once you start the DMA. Okay, so in the KL25Z, actually there is a DMA as well. All right, so if you look in your data sheet, you will see that it has 4 different channels, okay, for each DMA block. All right, so it is quite a comprehensive uh, controller with a lot of features. Okay, initially I wanted to have one lab to do this DMA. All right, but then I realized that if then everything gets pushed back, then your whole OS and everything gets pushed back. So that is why this one I did not do. All right, but I am going to prepare some additional notes and information and how to further use the KL25Z. Okay, once that is done, I will share with you, and then yeah, probably when module's over and you're free, you can have a look at it. Okay, now so that wraps up the DMA part. Okay, so I'm not going into too much detail, but I think it's just a bit more extra than what you cover in your EPP2. All right, but the whole idea, as long as you understand that if you have a DMA block, all right, it is something that you can use to your advantage when you need very fast data transfer. Okay, the Arduino Uno doesn't have it, okay, but the KL25Z has it. All right, I mean the Arduino range of controllers, the higher end ones have it. All right, so if you think that your system that or whatever that you are working on would benefit with this kind of fast data transfer happening, then you probably want to look for a controller that has a DMA block already built in, and that can help you. All right. So it's always important to have a good overview of the hardware and what you are dealing with, and to see whether it is suitable for whatever project you're working on. All right. So that I mean, here when you do the modules and all, of course, we give you a board and you work with the board. Okay, but if you're working on your own project, FYP or Europe or something like that, okay, you want to look ahead to see what are the things you need to do and whether your device can support it in an easier way. Or that many students I've seen is they start out with something that they're familiar with, which is fine, but then along the way they realize that it is not as capable as compared to what the things they want to do, rather than they're stuck because you already spent quite a amount of time working on it, and then now you do not know whether you want to go back and change the controller or work with this current controller and try to do some hack around it. All right, so it's always good to know what you really need and choose the correct controller or platform that can fulfill the system's requirement before you start the project. Okay. Okay, now let's look at another important thing. So this watchdog timer. Okay, watchdog timer is something that is generally found in most controllers. Okay, even the simple ones like Arduino Unos will have it, and the more high-end ones like KL25 that definitely have it. All right. So what is the idea of a watchdog timer? It is to help uh, the system in the event that it reaches a point of failure. Okay, so what do you mean fail? That means things like priority inversion, deadlocks, okay, some major hardware or software failure that the system cannot recover from. All right. Those of you who use Windows, we know it's the blue screen, correct? Or in your handphone, sometimes suddenly it just hangs, and then after a while, you see that it reboots. All right. So how come your handphone, when it suddenly hang and it reaches a point where nothing works, correct? You can't press the button, nothing happens, then suddenly it just reboot by itself. All right. So that is where the watchdog timer comes in. All right, to sort of provide a safety net, okay, and allow the system to reboot to a safe mode. Okay, so what is a watchdog timer? So generally, what we say is just like a hardware timer, okay, and what it will do is you preload it with a particular value. Okay, so let's say you start out with 0xFFFF, okay, and it will count down to 0. But the idea is you do not want it to count down to 0. Okay, so what you must do is you must periodically go in and issue a reset. So in the software, there must be some routine that is running, some periodic interrupt that is running, where you go in and reset this watchdog timer. Okay, if for some reason the system hang, you cannot execute the code, something really bad happens, your hardware will still carry on, correct? Because as long as the processor is powered, the clock is running, the hardware will still run. So the watchdog timer will count down to 0. When it counts down to 0, then it will issue a reset to the processor, and that is where the reboot will come. Okay, so that is what or how the watchdog timer helps us in the event where something really bad happens and you can't execute the code, that even the periodic interrupt handler also cannot run, then something is really bad. Okay, so instead of waiting for the user to do something, you reboot the system and let it come back to a safe starting point. All right. So that is the idea of the watchdog timer. All right. I mean, generally we do not really use it that much. Okay, but if you're talking about a final product that you're going to implement or you're going to market, it's good to look into this watchdog timer concept so that you know that in the event that something happens, it is able to reboot and at least go back to a proper state. Okay, so of course, watchdog timer only can sort of, it's not a foolproof mechanism, all right, because it does not catch all cases of system being hanged. All right. So, for example, in the case of a deadlock or priority inversion, it is something that is still at a task level, but the interrupt may still happen. All right, the interrupt can still happen. The watchdog timer can still run and reset the watchdog timer, and then you don't reset. Correct. So uh, it is not the case where all system failures will be captured by this. So you need to look at other mechanisms. All right. So if you do more research in this area of software development and safety critical applications, you will see that there are a lot of other strategies that have been discussed on how to catch deadlocks, how to look at priority inversion, and how to detect them to reset the system or reboot the system or put it into a safe state. Okay, so watchdog timer is just one aspect where the system has reached a point where it can't even execute instructions. Okay, but it doesn't mean that if there's no watchdog timer triggered, that means the system is fine. No. It could still be in a deadlock situation. It could still be in some priority inversion situation and so on. Okay. Okay, so let's look at some case studies in the past, all right, that are quite prominent if you look at the literature. Okay, so in this example here, it is a deep space probe, okay, that was launched, okay, and what happened was after a few months, there was some software exception, okay, that caused the thruster to fire for 11 minutes, all right, and this caused this probe to spin, all right, and rotate at a very fast rate, okay, and what happened was a lot of fuel was wasted in this moment, all right, and because of that they were not able to successfully complete the mission because it ran out of fuel. Okay, so you can see that a software bug, okay, caused this, and the important thing I say is it happened after many months of operation. That means even though we test our code, we do everything, there could always be some corner case or some event happening that we may not be able to catch. All right, and then it causes something like this. So what can we do to, as quickly as possible, do some override to prevent something like this from causing more damage? All right, so these are things that we need to think about, all right, when we are designing system. All right, I mean, if you think about it, let's say your robot that you're doing, all right, uh, if let's say you say every time I press the forward button, it will move forward by itself until I press the stop. Okay, so what if you press the forward button and by the time you press the stop, the Bluetooth connection is lost? So the robot will just keep on going and banging and bulldozing its way through everything, correct? Until it becomes damaged to a point where it cannot move. Okay, so these are things that, of course, you can think about when you are working on other projects as well. How do I put in some safety critical aspect? Okay, that if after some time the same activity is going on for too long, something is wrong. I need to stop. I need to check. Okay, something like that. Okay, so this is to just again give you some ideas that as engineers when you graduate, how do you improve the quality of the work that you're going to deliver? Okay, so another example is a classic example in most RTOS literature, all right, where there was a priority inversion, okay, on this Mars pathfinder. Okay, so as you know, these kind of space probes, usually they send uh, to the Mars or some other planet to do some experiments. So as experiments, what they will do, they'll collect samples, they'll do some analysis and send the data back. All right. So what happened was there was some sort of a priority inversion between a communication task and a science task. That means some experimental task. All right. And because of that, the system started going haywire. All right. But that is where the watchdog timer was able to kick in and bring it back to a proper reset state. Okay, and interestingly they were able to upload a new code, okay, from remotely, okay, from earth they were able to upload a new code and fix the problem. All right, so this is also another important thing. If you look at all our systems nowadays, they have the ability to remotely download. You look at your phone, you can always download a new upgrade and install it. Correct, so that is also another sort of safety aspect that we can put into the system, correct, when we build it. That means after the product has already been been released to the customer. All right, and you know that there are issues. How can you resolve it? Is you provide some upgrade, some patches. Correct. So your architecture originally must already have the framework to support this process. Okay, so that is another important thing. Okay, so this is another classic example to illustrate the communications issues that engineers have, okay, with the end user. Okay, so if you remember the Desert Shield, okay, maybe you don't remember, okay, too young at the time. Okay, Operation Desert Shield was again a US military invasion, and in that time they had this idea of a Patriot missile system where any incoming missile you can counter it with another missile and blow it up before it hits the ground. All right, so it's a highly complex system. All right, and what it will do is you will use the velocity of its target, okay, and current time to predict. Okay, so when the enemy fires a missile, you will track the missile to predict where it will land. Okay, so the engineers who designed the system, okay, knew there was a bug. Okay, because in this case the timing is very critical. Correct, timing is very critical. So they knew that this internal clock would have some drift, okay, that will cause some inaccuracies. All right, and even though the bug was known, okay, what the soldiers were told is they just need to regularly reboot the system. Okay, so this is again a classic communication error, correct, where engineers say regularly, but what does the normal person interpret regularly as? All right, so without clear instructions, all right, the soldiers who were using the system were not able to interpret what is meant by regularly. Correct, so they left it on for more than 100 hours. All right, and what happened was when there was an incoming missile from the enemy side, okay, the system miscalculated it that will land in some open field because of a drift. So you can see the drift is very small, but yet it's so significant because you're talking about a missile system. Correct, and eventually because of this drift, it actually landed on a US airfield, killing their soldiers. All right, so again, you can see it is a very simple thing which could have been easily resolved if the engineers just put in an auto reboot prompt. Correct, that means if you know that the system tolerance is maybe 0.1 second, so the moment the drift is 0.1 second, you automatically issue a warning that you cannot use the system until you reboot. So that would at least force the user to issue a reboot before you can continue using, just like your Windows, correct? Okay, after some critical update, you can't use it unless you say you reboot the system, then only you can use it. So if they implemented something as simple as that, even though there is a bug in the timing hardware or the timing system, it is still a usable system because you are forcing the user to do a regular reboot. All right, so again, these are things that you need to think about, okay, because as engineers we tend to think in a certain way, all right, but the end users may not have the same thought. All right, so that is where we need to be mindful to make sure that the end user who uses the system knows the easiest way to use it, all right, without having any confusion, okay, about or what are the steps involved or things like that. Okay, so that is so these are some of the case studies that I'm just discussing with you to, I think, bring to awareness how as software developers or computer engineers, the things that we do can have a big impact, all right, on many people's lives. So we need to be very careful of making sure that we do our job correctly. Okay, so that brings us to the end. Okay, so let me first talk about the exam, okay, and then I'll talk about the project. Okay, so for the exam, it will be similar to our midterm, all right, where we have the Luminous quiz plus Zoom proctoring, all right, so same idea. It will be closed book with standard RTOS reference sheet. Okay, so there will be no cheat sheet for you all to use. Okay, I will provide a standard RTOS reference sheet. Okay, it should be a soft copy where I would extract out whatever is necessary in terms of the OS kernel calls and I'll put it there. Okay, and that is the only document you're allowed to reference. Okay, in terms of chapters, okay, we basically have to cover all. Okay, but let me just clarify that the topics that we covered in the first half, that means up to midterm, is only at the conceptual level. That means I will not ask you again how to configure the register to do this, how to set this particular bit, and so on. Okay, so all those things that we did in terms of the register configuration, hardware design, those will not be tested. Okay, when I say conceptual means what? That means you still need to know what is an interrupt. You still need to know what is a PWM or what is a UART signal and things like that. But I will not show you a PWM signal, say what is the duty cycle. So it will not be testing you at the hardware level or the register level. Okay, but the concepts you need to know. Okay, so that when you see a question on RTOS, and so for example, I might say there's data coming in on the UART port. Okay, so you need to know, okay, what is UART because you studied before, but I'm not going to ask you configure the register for this baud rate. No, that those kind of things will not be tested. Okay, so only the conceptual part you need to understand. There is no hardware, register configuration, and all those things that were covered in the midterm. So those low-level details will not be tested. All right, so the focus area will be anything from the RTOS onwards. Okay, RTOS onwards is the focus area. There will be short answer type questions. All right, there will be no MCQ. Okay, it will be all short answer type questions. All right, and there will be some answer boxes with word limits. All right, so and those are intentional. So for example, I might give you a question with some code, uh, and you're supposed to explain what would be the value of this particular variable when I execute this code. All right, so or how will this value change and so on. So those kind of questions, you're just supposed to give the numbers. How will the value change and so on. So in those cases, I will just give you a word limit or maybe 50 words or 100 words, just so that you give that answer that is focused on those. All right. So if you see answer boxes with word limits, that means they are intentional. That means I just want you to give me what I'm specifically asking for. That's all. All right. Besides that, there will also be analysis and writing of code. All right. So okay, analysis of code means what? That means I might give you some code snippets. Okay. So like if you look at the last tutorial where I put in some exam style questions, so that gives you the idea. That means I will give you some code, I will give you some background, okay, that this task was already created and things like that. Okay, explain maybe which task will run first, or explain the value that the semaphore will hold, something like that. Okay, so you'll be given some code and then you need to analyze the code and give your explanation. Then there might be some writing of code. So when you say writing of code, okay, you need to use just the simplified uh, approach. That means you won't need to declare all the variables, whatever I will specify in the question. Okay, that means if I say write the function to do this particular operation, then you just write that function alone. You don't need to worry about where to declare the variable. I need to include the header file, all those things don't need. Okay, so you just need to write whatever that I specifically ask you to write. Okay, so for example, if I say task 1 and task 2 are going to have this particular behavior using a particular semaphore, for example, then write the code to do this. Then you just write that code. Okay, I might say, okay, the semaphore, you don't need to create a semaphore, it's already created with this particular initial value. You just use the semaphore in your code. All right, so look at the question carefully, and when you write the code, you just need to write on what is specific, okay, based on what I'm asking about. All right, so that is basically the exam. Okay, the dates, I think you can check on the Luminous also. There's the date, and I think the official exam schedule also there's the date and the timing. All right, so what I will do now is I'll just give you all a short 5 minutes break to think through whatever questions you want to ask. All right. And then after coming from the break, I'll answer all the questions one shot. And at the same time, I'll go through the tutorial question, the last question on the address decoding. Okay. So I'll give you all a break first. Okay. 5 minutes, come back, and then we will go through all the questions that you have regarding the exam, and then I'll talk about the project as well. Okay. So let's go for a short break and then we'll come back. Okay. So welcome back. Okay, so there's a question here on any calculation question. Is there any question regarding calculations? All right, so calculations wise, I would say uh, the only calculations that you will see is those related topic on the scheduling, correct? Where we talked about how to schedule algorithm, schedule tasks based on specific algorithms. Okay, how do you calculate utilization and things like that. All right, so those are the parts where there were calculations involved. The rest of it will mostly focus on the concepts. Okay, so any other questions you want to ask about the exam? Okay, so all right, so basically we have completed the module. Okay, and through this module you have obtained extensive experience and knowledge. Okay, I hope. Okay, in both the embedded systems concepts as well as RTOS concepts. Okay, so if you are keen to be a TA for this module, I've created a Luminous survey. Okay, so if you go to your more 2271 now, okay, you will see that there is a survey created. Okay, so in that is called 2271 TA. You can just fill up the survey, all right, and once the semester has concluded, I will contact you. Okay. So again, if you have feedback about the module or the CEG program in general, you can let me know, all right, and we will see how to make it better or more engaging for the future. Okay, so right now, let me look. There's one more question. Okay, there is no cheat sheet allowed. Okay, so let me go back here. Okay, there's no cheat sheet. The only thing is I will provide you with a RTOS reference sheet. Okay, which will be a soft copy version. Okay, you all are not allowed to have your own cheat sheet. Okay, so it's a closed book exam. I will provide a reference sheet for the RTOS kernel course. Okay. All right. So let me move on to the last question on the tutorial. Okay, for the address decoding. Okay, and then I'll just talk a bit about the project assessment part before we end. Okay, screen recording is standard. Standard. All exams, I think, it's now a standard thing that you do screen recording. Okay, but I will send out the SOP. All right, just like how for the midterm, I'll send out the SOP again just to make sure everybody is aligned on this screen recording. I mean the whole process. Okay, what will happen? Again, screen recording. Please check. All right. Uh, I will update the SOP. You do not need to upload the screen recording to Luminous, but you need to upload it or put it in some shared folder and send us the link. All right. So usually it's either Google Drive or Dropbox. You need to put it in some folder and then update the link of where you have put your video in the Luminous. All right. And then, like I said before, all these are subject to random audits by the school. All right, so you need to make sure that all your screen recordings are there. Okay, for the midterms, some of you had issues. All right, so you need to resolve all your issues to make sure that screen recording goes on smoothly for that full 2 hours of the exam. All right. So if you have space issues, storage issues, you need to look at how to resolve it. Okay, at least for all those screen recording to be captured correctly. All right. Okay, so let me move on to the tutorial question first. So I'm just going to go through the last question, which is on the address decoding part. Okay, just to make sure you understand how to do this. Okay, and then I will just talk a bit on the project. Okay, so in this question, you are given this memory map. Okay, and from this memory map, you want to get a feel for how to design it. Okay, so let me share the whole screen right now. Okay, so how do we go about designing it? Okay, so the first step is you want to know the starting and ending address for each of the memory devices that you have. Okay, so let's list them down. So you have a 2K ROM 1, okay, then you have 8K RAM 1, 8K RAM 2, and 16K RAM 3. Okay, now what you need to do is you need to now list down the starting and ending of each of these. Okay, so what is the start address and what is the ending address? Now let's look at it one by one. So for the 2K ROM 1, we know that it's starting at 0, 0, 0, 0, 0. So what is the ending address? Okay, so the ending address will be 2K from this, correct? So if you open up your calculator, okay, if you put your calculator in your handheld calculator as well, 2K is 2048, which is hex 800. Okay, that means if it's hex 800, that means the ending address would be 0x07FF. Okay, because hex 800 is total number of locations, so inclusive of the starting and ending, you have 0000 to 07FF. So this ending point is 07FF. Okay, now we can do the same thing for the rest. But for 8K RAM 2, what do you have? If for 8K RAM 2, you know the ending address. So this ending address is 0x9FFF. Okay, so now I need to go back 8K to know the starting point. So what is 8K? So if you look at 8K, it is 8192, which is hex 2000. So hex 2000. So if I were to take the ending point, which is 9FFF, okay, and I subtract 2000, okay, what do I get? I get 7FFF. That means the starting point of this is actually 0x8000 because it is inclusive. Right, the 8K space is from 8000 to 9FFF. All right, so similarly, so if this is 8000, that means the 8K RAM 1 ended at 7FFF. So this ended at 7FFF and it started 8K back, so that would be 6000. Okay, then you can do the same thing for the 16K RAM 3, which is FFFF. So going back 60K, you will see the starting address is C000. Okay, so the first step is this, getting the starting and ending address in place, all right, so that you understand where we start from and where we end from for each of these devices. All right, so again, conceptually, what we want, that means what we want to design is an address decoder where this full 16-bit Okay, so from the 16-bit address, so this is 16-bit address that comes in. Okay, we will not necessarily use all 16 bits, but using certain number of address bits, okay, through this address decoder circuit, I must be able to generate 4 chip select. Okay, the 4 chip select are the mapping for the 4 different chips that I have here. All right, now the next step is to design the circuitry. I must first understand the logic of mapping the address bits to specific devices. Okay, so how do I do that? Okay, so for that you need to draw a table where, since we know that it's a 16-bit address bus, okay, so let's look at the addresses: A15, A14, A13, A12, A11, A10, A9, A8, A7. Okay, so I'm not going to draw everything, but okay, so now let's look at the first device. The first device is the 2K ROM. All right, so for this, I'm going to focus on the start address and the end address. Okay, so what is the starting address for the 2K ROM? You know, the starting address is 0000 up to 07FF. Okay, so this will be 0, all the way will be 0 up to 07FF. So 07 means this is 0000, and 7 is 0111 and 1 all the way. Correct. So you can see that from the starting address and ending address, these are the complete range of addresses that were mapped to 2K ROM. Okay, the 2K ROM chip. So what we need to do is those address lines that are changing, we can ignore. Those address lines that are constant, we keep. So if you look at this two addresses, start and end, the two from A10 onwards is where the address bits are going to change. But A15 to A11, they are constant, they are always 0. Okay, so that is the idea. The concept is I want to look at what is constant throughout this entire access. Okay, so I know that when I'm trying to access any address here in this entire range from 0000 to 07FF, A15 to A11 will always be 0. Only A10 down to A0 will keep changing. Okay, A15 to A11 will always be 0. Okay, so since I know that, I can now say that I can use these 5 bits to select this ROM chip here. Okay, so that is the same thinking we're going to apply, okay, for each chip. Look at what is changing, look at what is constant. Okay, whatever is changing we discard, and whatever is constant we will keep. Okay, now let's look at the next chip. Okay, then you can have a better idea. So the next one is 8K RAM 1. Okay, so let's look at the start and the end. Okay. Okay, so for 8K RAM 1, the starting is 6000 to 7FFF. So let's put in the numbers here. So 6 is 0, 1, 1, 0, 0, 0, 0, 0, 0, 2, 7FFF. So 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so this is 6000 to 7FFF. Okay, and you can see again what is constant and what is changing. From A12 onwards, all the bits below here are changing. Only A15, A14, A13 are constant, which are 0, 1, 1, 1. So 0, 1, 1. Okay, so that tells me that if I just look at the first three bits 0, 1, 1, that will map to my 8K RAM1 chip. Okay, so let's do the same thing for the next one, 8K RAM2. So I got to start and I got to end here. So for the 8K RAM2 chip, it is from 8000 to 9FFF. Okay, so 8000 is 1000 all the way 0 to 9FFF. So it's 10011111. Okay, and the same thing you observe that the bits, okay, from A12 down to A0 are the ones that are going to change, whereas the upper three bits are 100. They are always constant while I'm accessing this particular device. Okay, so you can see it's the same pattern. As long as you understand this idea, then it's easy to do it. All right, and then one more here. There is the last one is 16K RAM 3. Okay, so let me put here start and the end. Okay, so the start is C000. So C is 11000000 up to FFFF. So 1111. So in this you can see that only the upper two bits, okay, the upper two bits are constant. The lower bits are all changing. All right, so the whole idea is we want to look at bits that are constant while I'm performing this memory access, because if they're constant, okay, that means I know that by just looking at these bits I can activate the device that I'm supposed to talk to. All right, so that is the thinking. So now that I have all of this, I can now go ahead to design my circuit. All right, so let's look at how the solution is. So I'm just going to show you one particular solution only. All right, using a 3 to 8 decoder. You may have other solutions you can think about as well that might work just as well. All right, so there is no fixed solution. You may have different ideas depending on what you want to do. Now in this case, what I'm doing here is so the first thing here is the question now specifically mentioned whether the chip select of the devices are active low, active high. So in this case, I have assumed active low for all. Okay, so in this case, I have assumed that it's active low chip select for all devices. All right, that means I need to have a 0, then only that particular bit will be, or chip will be activated. Now let's look at what we have here. So I have the 3 to 8 decoder. Okay, so the 3 to 8 decoder is here, and what I'm going to have here is A15, A14, A13. All right, so now let's look at how I've connected and relate it back. If, okay, when A for 15, 14, and 13 are all three are 0, 0, 0, what will happen? This line will be activated. Okay, and this is also a active low output, so this will be a 0. The rest will be a 1. Okay, so in this case, my 3 to 8 decoder is also chosen to be an active low output device. So when I say 001, sorry, 000, Okay, so this is the most, okay, since it's 210, this is the most significant bit, this is the least significant bit. Okay, so when it's 000, line 0 will be activated. So when line 0 is activated, okay, for just looking at this, what do I see? I see that I satisfy the condition that this is 0, this is 0, this is 0. Okay, but I still need A12 and A11 to be 0. Correct, I still need A12 and A11 to be 0. So in this case, I put A12 and A11 to an OR gate. So when both of these are 0, okay, when both of these are 0, then only this one can be 0. And when both of these are 0, then only this one can be 0. So they activate the ROM1 chip select. Okay, so you can see that this ROM1 chip select will be 0 only when A15 down to A11 are all equal to 0. Okay, so that is how I activate the chip select for ROM1. Now, for chip select of RAM1 and RAM2, okay, is fairly easy because you already have a 3 to 8 decoder and you only need 3 bits. So it's 0, 1, 1 and 1, 0, 0. Alright, so you see down here, the 3 bits here are 0, 1, 1 and 1, 0, 0. So when the A15, A14, A13 are 0, 1, 1, okay, so when it's 0, 1, 1 over here, it is line 3. Okay, this will map to line 3. So you chip select of RAM1 will be activated. When it's 1, 0, 0, it will be line 4. Okay, so chip select of RAM2 will be activated. Okay, now the next one is this. The last one, 16K RAM3. For the 16K RAM3, basically, I need both the first two bits to be 115 and 14. Okay, the last bit A13 is still changing. Correct? So I'm only going to look at A15, A14. Now, so in this case, what do I have? Okay, in this case, that means I must look at the possibility of 1, 1, 0 and 1, 1, 1. In both cases, I want the chip select of RAM3 to be activated. So when it's 110, line 6 gets activated. When it's 111, line 7 gets activated. But I want both of this to activate RAM3, correct? Because RAM3 is occupying the full 8K range. Okay, so what I need to do is when this is 0, also I want activation. When this is 0, I also want activation. So since I connect it to an AND gate, when either input is 0, the output will be 0. So RAM3 will be activated. Okay, so this is just one possible example only. All right. Okay. You can definitely think of other solutions using other gates, or instead of active low, you say I want everything to be active high, then your solution might also change. All right. So it's as long as the thinking is correct. That means I want to activate the chip select of a particular pin when certain conditions in the address bits are fulfilled. So the whole idea is I use those address bits to make the decisions for me. All right, and that will help me to activate the correct chip based on the address information. Okay, so that is basically the question here, okay, for the address decoding. And I wanted to just go through this in the class. Okay, in the tutorial later on, you will go through the other first 3 questions from the tutorial. All right, so the first 3 questions I think are a bit more doable. All right, but this one I wanted to go through with everybody so that you understand how to do it. Okay, so any questions on this? I mean, something different, something new. It probably takes a while for you to go through and understand the concept, okay, and then you know how to interpret. Okay, so I mean, definitely you might have questions later on when you go through the tutorial again. Okay, and try to do it on your own. Okay, then if you have questions, you can always contact me. Okay, we can discuss. Okay, so later on the tutorial you will still have, okay, this week and next week. Okay, next week's tutorial will be optional. Okay, the tutors will still be there. Okay, if you have things you want to clarify, you can log in and you can clarify. Okay, if you come, you can still get any participation points if you still are lacking. All right, but it's not compulsory, so attendance will not be taken for next week's tutorial. All right. Okay, so before we end, let me just brief you just one more bit on the assessment. I will send a more detailed announcement on how the assessment will be done next week for the project. But just one thing to clarify, as some students have been asking me. Yeah, let me find the document. Okay, so for the challenge runs, okay, the first one is the same that I had last year. All right, so if you need any help with setting it up, you can ask the TAs to help you set up, all right, using the codes. All right, but it's the exact same setup and the route as last year. Okay, so you can look through some of the videos from my website, all right, and you can see how they did. All right. Um, so this distancing, okay, is just some, is more or less constant, okay, but maybe a bit off, but it is fine because anyway you are in control of it. Okay, you're in control of the robot, so uh, that as long as you know how to control the robot in the proper way, it's fine. Okay, some of you have been asking whether there is any particular way in which the distance must be controlled or when to stop after I move forward. All right, so that is up to you to decide. That means if I press, let's say, move forward button, some of you may say that every time I move forward, I will move a certain distance and then I will stop. Some of you may program it such that I press the button, it will just keep moving forward until I press the stop button. Either way is fine. Okay, whichever way you want to implement is up to you to decide. As long as you know how to control your own robot to complete the maze, that is what is more important. All right, how you want to look at the final details, that is up to you. All right, so in terms of the requirements checklist, as long as you can demonstrate that you can move straight, you can turn right, you can control the LEDs and so on, that is fine. Whether you move forward continuously or you just move a bit by bit, all that is fine. All right, so I think that is one of the things that people are asking. Then the next one is,
Can I ask a question?
yeah, sure.
It's on RTOS. Is it stupid to do a switch case around a thread flag that we get? Like let's say in the thread, right, then we use a switch case on a get thread flag or something.
No, I don't think you should be doing that, because the whole idea of the thread flag is you wait for the flag to be set. So if you want, you can either wait for individual flags to be set, or I mean, under the attributes you can say flags all or flags any, correct? So you can choose to uh, configure your task based on which flags to be set, and then you execute. Correct.
So
Okay,
this means the flag is just purely to tell it when to start, but it doesn't dictate what it does. So that's dictated by the message queue.
okay, message queue is different from the thread flags. Correct. In message queue, you are sending some information, and the other person is supposed to receive and decode the information, and then decide what to do next. Okay, so if you use message queue, then when the task receives the message and it unblocks, you can also decode the message at the same time and decide what to do. If you use the flags concept, then it's also fine. Only thing is the flags will, when somebody else sets the flag, then the task that is waiting for the flag will be unblocked, and then you can decide what to do, maybe based on some other global variable or something.
Okay, so the flag cannot decide. The flag cannot tell the task what to do. It can only tell it to start, and that's all.
I mean, if you decide to say that I have 31 flags, and if I say that when this particular flag is set, I will do something. With this particular flag, I will do something. Also can, correct? That means when you write the code, okay, then you must write it in a way that when some flag happens, activated, some function is called. All right, but then the issue then comes is when the first flag is not set, and then how do you move on to the second one and so on. Correct.
Okay,
So
understand. All right, thank you, Prof.
Okay, so I mean, you can think of whichever way that you feel is doable, okay, and manageable to fulfill certain objective. Correct. I mean, like I said, what you have is a very powerful tool in terms of the OS. Okay, try to think of how you can capitalize on it, just like the DMA concept. Correct. It's like having a DMA, but you still write a loop to move data around, then it's a waste, even though it still works. All right, so it's the same thing. Okay, you can go back to your single threaded mode of thinking and get certain things done as well. All right, but if you can do it in a more efficient way or elegant way, it's fine. All right, I'm not going to the grading will not be based on that level of implementation. All right, so even if you do something that is not usually done in the OS concept, it is still fine as long as you fulfill the requirements of the project. Okay, but like I said, try to think of how you can capitalize on what the OS has to offer. Okay, so just one more clarification here for the second challenge run here. Okay, there is another cone at the back here of the robot. All right, that means once a robot moves right, the green arrow, it detects and it goes around. Okay, it comes back and it detects a second cone and then it stops. Okay, so there will be two cones here. All right, so one cone to detect or to indicate the obstacle, and then you go around it, and when you come back, you detect the second obstacle and then you stop. So this is the self-driving mode. That means on your app, you are just supposed to press start or something, and it will just go by itself. Yeah, once it comes back, that's it. There's nothing else to do after that. So as long as you come back and you stop there, then it's fine.
Prof, can I ask you a question?
Yeah.
For the running LED, it means is one LED for the green LED, then from left to right, then go back from left to right, or it's like increasing.
Yeah, correct.
So it's just one LED. It's not like first LED light up, then first and second light up, then first 1, 2, 3 light up.
It's one at a time.
One at a time. Then for the blinking, just any of the green LED flash twice will do.
Yeah.
When it's connected to Bluetooth.
Yeah.
Okay, sure. If all connect, can or not? All light up at the same time. No? Blink twice.
Sorry again?
If now all LED, all green light, it means when I connect Bluetooth, right? All the green LED blink twice. Is it possible? Is it okay?
Yeah, it's also okay.
Okay, sure. Thank you.
Okay, so for the leaderboard ranking here, okay, okay, so this is someone challenge board 2. Okay, never mind. Let me change this later. Okay, so the team that comes in last definitely will not get 0. Okay, so the team that comes in first will get the maximum marks. Okay, and then from there we will sort of have a gradual runoff. Okay, but the team that comes along the way, I will stop somewhere near the halfway mark. Okay, that means minimum you can expect to get out of 25 is at least about 12. Okay, for both the challenge. All right, it's not, you will not go down all the way to 0.
Hello, Prof.
Yeah.
Oh yeah, also for challenge run 2, right? Like it's separate from challenge run, is it? I assume. So like we get to place it down first and then.
Yeah, it's 2 separate challenge.
Okay, all right. Thanks.
Okay,
Prof, for the challenge run 2, right? That one you must start inside the box and end inside the box.
Yes.
Must
So, sorry?
like if like you're outside the box, you end outside the box, then there's some penalty or something.
Yeah, so I will come up with the grading criteria by this week so that you know, okay, if you, let's say while you are turning, you hit the obstacle, what happens? If you stop outside the box, what happens, or things like that. So there will be penalty marks for that.
Oh, okay, thanks.
Okay, so for B3, the robot must stop all movement, command is sent. Okay, this is just to make sure that when your system, like for example, if you say start, okay, and then it moves, and then you press either it stop by itself or you press another button stop, okay, it should stop, and then it should not have any other additional movement after the robot stop. Okay, so it's just to make sure that if I already say stop, then it must stop and not do any other movement. Okay, so it's not to do with whether you hold the button or let go the button. It's just to make sure that if I don't send anything, the robot should not move. Okay, so are we allowed to modify the robot in between the 2 challenge? So when you say modify, means I would assume you want to upload a new software or something. Okay, so that is fine. All right, so it will be 2 separate challenges. Okay, so you can upload different code to your robot for the 2 different challenges. That is fine.
Prof, is there any details on when the demo will be?
Yeah, it will be next Friday. I will list out the sequence and the timing all by this week.
Thank you.
Okay, the submission of report and the video, I will let me see. Yeah, you will have 1 more week. That means 23rd April. Okay, so I'll give you 1 more week after next Friday to finish up the submission of your report and your video.
Prof, on the actual day, right, we can do calibration on the spot, right, for like the self-driving part.
Yeah, can. Okay, so another important thing is please make sure you understand, especially for the this challenge run 1, the arrows indicate that you're supposed to go around the cone. Okay, so if you look at the first part here, after I go up and down the ramp, I'm supposed to turn left, go around the cone, go through 2 cones, then turn left again, go around the cone, then go up and down, and then do the figure 8. So this figure 8, okay, maybe it's not figure 8, it's more like an S. Is either you go to the right and then you go this way, or you go to the left and then you go the other way. Either way is fine. All right, and then you go behind the pillar back to the ending point. Okay, so you can look through the videos, okay, of the past students to have a look at how they did it. All right, so this is important. All right, to make sure you do it correctly. Okay, because if you miss the turn, I mean, instead of, let's say, going around to the left side, you take a shortcut and go to the right, there will also be penalty marks. All right, that means you're taking a shorter route compared to the rest. Okay, so please make sure when you practice, you follow the sequence exactly. Okay, where you're supposed to go around, where you're supposed to go through, and so on. Okay, for the actual assessment next Friday, your whole team doesn't need to be there. Okay, as long as someone from your team is there to present and do it, it's fine. Okay, so if you can't be there for the whole duration, then ask somebody from your team to take over and do it. Okay. See anything else? Yeah. So another thing is, most students usually want to have a trial run, okay, before the actual run. Okay, that means when it's your turn, most of them will say, okay, can I have one trial run first? Okay. From past experience, I'm just sharing that most students do very well in the trial run, and the actual run, you just commit suicide and fall off the ramp. Okay, so it's up to you. Okay, I think generally you tend to be more relaxed when you say it's a trial run. Okay, when it's actual run, your heart beats a bit more faster. All right, and then you panic and then you press the wrong button. Okay, so you will need to clarify beforehand with me, and the TAs will be there to help as well. Okay, so before you start, you need to clarify clearly. Okay, I will have some mechanism there to make sure there's no miscommunication, that it is a trial run or actual run. Okay, because again, I do not want any miscommunication that you say it's a trial run, and then after the run you realize, wow, you had a fantastic run, and then you say, oh no, this is actually supposed to be the actual run. No. Okay, you cannot change your mind halfway. All right, so if you start off and you say that this is going to be a test run, then it's going to be a test run. All right, so there's no timing. We're not going to check whether you hit anything or whatever. But once you say it's the actual run, then we will follow the robot around to make sure that you're following through on the actual route. Okay, and that we're also taking the timing. Okay, for each of the challenge runs, you have two attempts, two actual attempts. Okay, where you will check and take note of all of this. All right. So of course, in between, if you want a trial run, we can still give you a trial run, either before or in between the two attempts. That is fine. Okay. So just be very clear that your trial run is a trial run. You cannot change your mind halfway through the trial run and say, can I make this actual run? No. Okay. So before you start, you need to clarify and be clear whether it's a trial or actual, and then we will follow on that. Yeah, okay, so the deadline is also mentioned here. All project related material will be 23rd April. Okay, so I'll create the submission folders and I'll tell you how to submit. Okay, so it will be this 1 week after the presentation, I mean the demo. Okay, so anything else, you can stay back and ask. Okay, those who want to stay back and ask. If not, that's all I have. All right, so thank you very much. Okay, and I will see you all next week for the final run.